So folks, in this example, we're asked to compute the mass of a box. And we're told that this box D, it has certain bounds. And in this case, all of the bounds are going to give us a nice rectangular prism for the total box. And then the density of the box decreases linearly with the height of the box. So this is the function right here that tells you how dense this box is. So when z is 0, when we're down at the base of this box, it's got a heavier density than we're up towards the top of this box. And we're asked to compute the mass of this box. So we said before that we could think of, I'm getting some sort of weird feedback, there we go, that the mass is equal to the triple integral over the region D of your density function per unit volume. This integral, the way you would compute this integral as written is you would go ahead and chop the region up into a bunch of sub-rectangular prisms, then take that representative point from the rectangular prism, evaluate it in the function, do that for all of your rectangular prisms, add up the results. And then what you would do is you would look at the limit of that expression. And that's fairly tedious to do. But just as we saw in the multivariate function for two variables, we can use something called Fubini's theorem that says, hey, rather than evaluating this triple integral, we can evaluate a triple iterated integral. So what I'm going to do is I'm going to break this up as an integral from here to here to here of f of x, y, z, and we're going to evaluate instead d, and I'll start off with dz, dy, dx. There's many ways I could do this, folks, and we'll explain this more in class. But what I'm doing is I'm setting up a triple integral where this is going to be from z equals something to z equals something, and we'll do the same thing for y's, and we'll do the same thing for x's. So it's important to me that you recognize that this object right here I've got these three integral bars sort of bunched together. That is a triple integral. But in many cases, and all of the cases we'll be looking at in this class, we will be able to evaluate our triple integrals as a triple iterated integral. And that's going to make it much easier, and especially in this case, it's going to make it more easy to evaluate the function. So let's give this a shot here, folks. The first thing you need to do is you need to start thinking about sketching your regions. Now, in this case, it is impossible for us to sketch this function, right? We're not going to draw this function in R4. We can't do it. But instead, we're simply going to sketch the region D, which is our domain space here. That's all we're going to sketch. So this region D, we're told, is this box, and we're not going to have too hard of a time constructing this box. Let's see here. The x values go between 0 and 3. The y values go between 0 and 3. So in this case, it has a square base. And the z values go between 0 and 1. And I'm going to exaggerate that slightly just to make that easier to see. And so here we have our region D that we're going to be working with here. So let me as often is the case, folks, I often draw these regions twice, once to kind of get a general intuition what they look like, and then once to clean it up. So let me draw this a little bit nicer here. So here we've got x, here we've got y, here we've got z. This is our region D, folks. This is very important that you realize that we're talking about the region that we're integrating over. This function lives in R4. If we wanted to think about its graph, it lives in R4, and I am not sketching that at all. I am simply sketching the region for which we're integrating over. Okay? And let's see here. We had x going from 1, 2 to 3, 1, 2, 3, so it's 3, that's a 3, and z was going from 0 to 1. Okay. So what we're saying here, folks, is, and this is a huge time saver, is rather than subdividing this up into a bunch of rectangular prisms and then taking a representative point from each one and then looking at the limit as we continue to subdivide that, we can go ahead and do these iterated integrals, which allows us to evaluate this as a bunch of Calc 1 integrals. So the z values, we notice, are going between z equals 0 and z equals 1. And the y values were going between y equals 0 and y equals 3. and the x values were going between x equals 0 and x equals 3. So folks, often that's too messy to write. I will encourage you for a while to make sure you're writing the x, y, and z there. Eventually, though, you can stop writing that. But the key thing is to notice the symmetry here, where my first integral for this function is going to be with respect to z. And so then the innermost integral has to be the bounds on z. And then my middle integral is with respect to y, so the bounds on that middle integral here, that sure enough fits with y, and then x here for the outer integral. So now we're ready to go ahead and evaluate this integral. That's going to be the triple integral from x equals 0 to x equals 3, from y equals 0 to y equals 3, and then from z equals 0 to z equals 1 of 2 minus z dz, and then dx dy. So evaluating that innermost integral gives us the integral from 0 to 3, from 0 to 3, and then here we're ready to evaluate this. This would be 2z minus 1/2 z squared, evaluated between 0 and 1, and then we'll have dy dx, and folks, I've got an error here. That should be, I've changed that order up. That should be dy dx, right? That should align with the middle integral. Okay. And as we continue to evaluate this, now we've just got sort of some calculations ahead of us. This would be 2 minus 1/2, so we get 3 halves. So this is the integral from 0 to 3, 0 to 3 of just the number 3 halves, dy dz, dy dx. And that integrates to be the integral from 0 to 3 of 3 halves y, evaluated from 0 to 3. And then all of that will be evaluated with respect to x. And then if we plug in the upper limits of integration and subtract the lower limits, let's see here, we end up with 9 halves. So that's the integral from 0 to 3 of 9 halves dx, which gives us 9 halves x evaluated between 0 and 3. So we get a what? Well, we get the number 27/3. How do we interpret this? Well, because we were told we're going to think about this as a density function. So this object is heavier, it's more dense at the base and less dense up towards where z is equal to 1. When we compute this triple integral that we were asked to find over this space here, that's going to give us the mass of the object. And so we don't have any units on this, but this would be 27/3 is the mass of the object. I hope that helps, folks. This should feel a little bit familiar in that it's exactly what we did in our double iterated integral case. And the key thing here, folks, so don't get too complacent, the key thing here that made this problem not too difficult is that every single one of my bounds was just a number, and I didn't have to think too hard about constructing my region D here. Constructing D was not too difficult in this case, but in other cases it will be far more difficult. So join me in the next video for some other applications.